Okay, so now we're going to be talking about exact differential equations. First, what is the meaning of exact? Well, first consider the differential. The differential is given by df is equal to fx dx plus fy dy. Now, suppose that f equals c, which c is some constant level curve, solves this differential. Then that means that df is equal to 0, because the partial derivative, or any derivative, with respect to a constant is always 0. As such, we get fx dx plus fy dy equal to 0. Now, the meaning of this is useful for solving stream functions when we're talking about maybe fluids. Now, suppose that we have m equal to fx and n equal to fy. We get that then that the definition of an exact differential equation is given by the following form. This form is called an exact differential equation form. And so to explain what an exact or what exact means, it means we have only one solution, and that is modeled by a constant level curve. So, but then in order to solve this differential equation, there's a few things we want to check. One is Clairaut's theorem. Clairaut's theorem states that for a given function, if it's twice differentiable, if it's continuous, if its second partial derivative is continuous, then we're able to model the following relation. The second partial derivative of partial x partial y is the same as the second derivative of partial f partial y partial x. This is just to say that the order in which you differentiate doesn't matter. Now, given that this above here is just partial f partial x, and that this is partial f partial y, then we can see immediately that by taking the partial derivative of the other variable and checking that this is in fact then it holds true, then we can actually use exact differential equation methods as enumerated by the following below. Second thing we have to check. We have to kind of have some function, and we can integrate either part. Because of Clairaut's theorem, it doesn't matter which part you integrate. We can integrate this part, we can integrate that part. The order in which you integrate doesn't necessarily matter, but sometimes one is easier to solve than the other. So it doesn't matter. This will equal some kind of answer 1 plus psi of the other variable. So in this case, this is psi of y, and this one is equal to psi of x. Now, psi of y or psi of x is called your stream function. Similar back in Calc 3 with what you might see as your potential function. This models fluids. Now, we have to solve for this. How do we do so? We take the partial derivative of the other variable. So let's say that we integrated m dx. We have to take the partial derivative of it. So it's going to be partial y of answer 1 plus psi prime of y. And we set that equal to the other part. Now, if we did this part right here, then we have to do the other one instead. But notice that solving wise, it's pretty much symmetrical. The same kind of variable. Now, fourth thing we have to do, we have to find this string function. Psi of y is equal to the integral of n minus partial y of answer 1 dy. Or if you're solving for psi of x, psi of m minus partial x answer 1 dx. Now, because of this notation is rather heavy, I'm just going to say this is answer 2 plus c. Similarly, answer 2 plus c. When we're done, we're able to find our differential again. Our differential would be some kind of combination of answer 1 plus answer 2 plus c. However, because we are trying to solve for the constant, or in a situation like this, the initial value problems here, or the initial values, if they're not given, we can leave it like this. However, if initial values are given, so if IC is given, then we have to actually give it in this form. Answer 1 plus answer 2. That way, we're able to solve for what our constant is when we plug in the numbers. So just to reiterate, an exact differential equation is one in which it satisfies and solves the exact, or is modeled by a differential. This differential has only one solution, hence the name exact, and we can solve for it using the following methods. In the next video, we're going to be talking about how to use this to solve for an exact differential equation. Okay, thank you.